Hello, everyone, and welcome to this talk about tools, tricks, and technologies for reaching a stutter-free 60 frames per second in Inside. My name is Kristian, and these two gentlemen are my colleagues, Erik and Søren. And I want to start out with doing a special mention to some of our colleagues at home, Lasse, Maria, and Michael, who has also been contributing to the systems we'll present in this talk. We will split it into 3 parts, and I'm going to start out with streaming the world of Inside without framerate stutters, and then Erik is going to take over with automation and profiling tools for ensuring a stable framerate, and Søren is finishing with 10 steps to get a 10x performance increase. A little bit of background. We are all 3 programmers from the company Playdead, and we made the games Limbo and Inside, and we have all 3 been with the company for quite a while and been on both projects. Today, we are only going to talk about Inside, as that has been made in Unity. We have sort of a pragma or dogma at Playdead where technology should never cause a distraction from the game experience. And for Inside, that means we should be able to complete the game from start to end without any loading screens, and we don't want any kind of artifacts caused by the streaming of content. And most importantly, we don't want any kind of frame rate stutters running at 60 frames per second on a current generation console. This has sort of a peculiar consequence that only when we do our job perfectly, no one will notice. So I'm going to talk a little bit how we have done this. So first part is we're going to split our content spatially and then save each of these parts into something we call a subscene. I'll take this sketch that looks similar to the game and then show how we will split this up into small parts. So we take the background and put it into a scene which we'll call the backdrop. And then we split the foreground into 2 sections, the left part, and we call that part tree and box, and it has an environment, which is the graphics. And then it has the box, which is the gameplay, and this is all the interactive elements, the collision, and anything that the player interacts with. It's in the gameplay scene. And then we do the same for the right side with the wall and bear trap environment, and we have the bear trap in the gameplay scene. And if you sort of imagine this being in the hierarchy of Unity, it would look something like this. And we have a master scene, as we call it. And then we have all the global objects like the camera and the boy and these things. And then all these assets we saw in the picture before with the mountains in the background, the trees, the box and the bear trap. They are then, as you can see, denoted with the boxes here. And instead of then saving these objects directly in the master scene, we save them out into separate scenes, which we call subscenes. And then we are able to load these scenes in and out of memory as the boy progresses through the game. In Inside, we have 250 of these subscenes, and we organize them in a hierarchy like this. So we have a scenes folder, which is just an empty transform. Then inside that, we have all the areas of the game, like forest, farm, city, and so on. And then inside those, we have individual puzzles. A game start, river with a dog, lake. And inside these hierarchies, we then have the actual subscenes that we saw before, the gameplay, the environment, and the backdrop. Each puzzle spans around 100 meters or 1 to 3 minutes of gameplay, so they are fairly small. And gameplay scenes are mutable, and they are marked dirty when they are activated. And in contrast, environment and backdrop scenes are what we call conceptually immutable, and that means that even though a tree can wave in the wind, the state of that scene would always be sort of consistent. So we utilize this to only reload the dirty gameplay scenes at respawn. So when the player progresses through the game, we activate the scenes that are inside the view frustum. And then in an area around the player, we have what we call a prepare zone. And when a scene enters the prepare zone, we load it in and prepare it to be activated when it finally hits the view frustum. Outside the prepare zone, the scenes are unloaded. And this is what it looks like in practice if we make a 2D top-down view of the first third of the game. We have a concept which we call potential visible set, which is a way for any part of the game to select which scenes are visible from that spot. And we do that by a frustrum, as you can see in the picture, the yellow. And any scene that overlaps this frustrum is going onto the list on the right side of the screen in the inspector. And then a level artist or level designer, he can go in to this specific point in the game and then look at it, and with his knowledge of the game, he would know that some of these scenes would not be visible. So he can manually exclude them, and you can see that with the red markings in the inspector. So this area goes from being 8 scenes to 5 potentially visible. Sometimes your content in your scene is not divided evenly, and in this example you can see all the geometry is in the lower right side of the scene, and we use voxelization to generate a 3D voxel grid inside the scene bounds. The figure is in 2D, but it's just for simplicity. But we do this voxel grid, and then we check each of these scene objects against the grid, and if there's an overlap, we mark that grid cell as active. And we do this at build time and serialize the result. Then at runtime, when we play the game, we test the view frustum against the scene bounds, and then if that is test positive, we then also test against this voxel representation. And only if the voxel representation is inside the view frustum, we actually activate the scene. We have one last concept to control whether an object is active or not, and that's something we call a bounce color. And it's a custom bounce which you put around an object, and then if that is inside the view frustum, we activate the object, otherwise it's inactive. Then sometimes in a game you have a wall, and even though an object is inside the view frustum, you can't actually see it. So to solve this, we use the concept of facing planes, which is a plane where only if the camera can see the front side of this plane, the object would be active. So in this case, the object is actually not active. And this is what it looks like in the scene view. And in this case, I've put a bounce color on a spotlight, and I've limited the bounce to be only where the light is actually hitting the ground, which is the only part of the light you can see. And in this case, the camera and the buoy is to the right of this facing plane, so therefore the light is active. We use bounce colors both for deactivating and activating single objects, but we also use it to subdivide the scenes even further. And as it can be seen in this example, we have divided this part of the game into these 5 sections, A, B, C, D, and E. And now I'll go through with an example what will happen if the player progresses through this area of the game. So the player starts out to the left of section A, and then every part of this scene is deactivated. Then the player enters section A, and that activates. He continues into section B, solves the puzzle in this area, returns into section A, drops down through the floor into section D, and now we can deactivate everything above the ceiling, because that can't be seen from that part of the game. Then the player progresses onwards to section E, solves the puzzle, and continues on. And now all these bounce colors are left in their inactive state. So let's try and do a recap of how we control if an object is active. If we take an expensive object, it has to pass all of these tests below. Is the object in a scene which is in the current potential visible set? If yes, we also check if the scene is actually inside the view frustum, and if it is, we then check if any of the active voxels are actually inside the view frustum. And if that's the case, we test if the bounce color subdivision of that area is set visible, and then finally we test if the bounce color for that specific object is set visible. And then only if all these 5 tests are positive, that object is active. That concludes how we were splitting things spatially. So now I'm going to move on to time slicing. And the concept is that if you have a chunk of work at a given frame, in this case frame 3, that would cause a stutter, we want to split this work over multiple frames. And then ideally, we actually also want to move some of this work to build time. And one way we do this is with a concept we call pre-awake. And it's a way to move expensive initialization code from the awake into this concept of pre-awake, which is a time-sliced way of doing this initialization. So the way it works is that you load the scene as inactive, and that means the awake has not been called yet for these objects. Then at build time, we have cached all these pre-awake scripts for this scene. And then before activating the scene, we call all of these pre-awakes, and we do that by calling only one pre-awake step for one object per frame. And then any code that is left inside the awake should be really fast code. And we actually also have an additional concept which we call late awake, which is a mono behavior you could put on a part of the hierarchy in a scene and then set the delay of frames after the scene has been activated that this part should activate. And that solves some of the last stutters we had in the game. So now I'll try to go through this step by step. So first of all, move work from runtime to the post-process scene callback in Unity, and then serialize the result. Then when the game starts, we utilize the initial loading and do pre-warming of shaders and expensive data structures and so on before we enter active gameplay. Then when the game starts up, all the scenes are in the unloaded state, and then we start loading a scene. So we do that with the asynchronous loading in Unity. And then when that is done, we start this time-sliced pre-awake as we saw before. And then when that's finished, we move the scene into the loaded and inactive state. And then it stays in this state for quite a while until it finally enters the view frustum and the scene gets activated. At this point, it's actually mostly a hollow scene with a lot of inactive bounce colors. And then as the player moves through the scene, each of these bounce colors activate and deactivate individually. And that means that the activation cost we get is at the granularity of a bounce color. Then as the player moves on, the scene gets deactivated again. And then finally, the scene gets unloaded. And also that we do in a time-sliced way, where we do a bottom-up destroy of small parts of the scene at a time. All these little chunks of work, we put those into a scheduler that has the responsibility to divide them evenly over frames, and it does that in a prioritized way, so that, for instance, unload has lower priority than activate of a scene. And now I'm going to talk a little bit about memory management, because as most of you probably know, if you're getting a garbage collect in Unity, you will also get a stutter, and we don't want those. So the way we got around this was having a zero garbage policy, and that basically means that we're not allowed to generate any kind of garbage on a per frame basis. And then also we should be able to make a complete playthrough of the game and only allocate 400 megabyte of heap space. And that requires quite a bit of work to do that, at least for our game. And then for the unmanaged memory, when we are doing all this loading and unloading of scenes as we progress through the game, we actually only remove the hierarchy nodes and not the assets that are referenced by these hierarchy nodes. And that's things like meshes and animations and so on. So after a scene has been unloaded, we do a manual destroy of each of these individual objects. And we do that manually because using the resources.unload unused assets during active gameplay would cause stutters. Then, of course, when the player dies or he loads a chapter, we utilize this point in time to do a GC collect and unload unused assets. And then we did some source code changes to Unity to improve the streaming performance. And one thing we did was a time slice of the scene integration, which is the last part of a scene getting loaded. Then we did a time-sliced initialization of the legacy animation system. We did optimizations to the game object activation. And we modified the garbage collection strategy of Mono to only collect when the heap is full. The default behavior is sort of a smart collect where it collects at around 20% heap usage. Then the most important takeaway points from this part of the presentation is making a streaming game in Unity stutter-free actually requires quite a bit of work. But if you do it, I would recommend split your game into small parts using something similar to the Subscene concept. Then load your scenes as inactive and use something similar to the pre-awake concept. Move work from start, on-enable, and awake to build time when possible. And then bounce colors works really well for manual occlusion culling and subdivision of scenes and reducing the granularity of activating and deactivating to the size of a bounce color. And then I'm gonna finish off with saying that we have a really close collaboration with Unity, and we try to improve the streaming performance and workflows based on all these lessons learned from the production of Inside. So now I'm gonna hand over to Erik.
Hi, my name is Erik, and I'm going to talk about some of the tools we used in our performance optimization of Inside. So the first tool I'm going to talk about is the Profile Runner, which is the tool we used in combination with the Unity Profiler to get a general overview of the performance of our game. So this is a view of the Unity Profiler, we more or less know it. It's a good tool for detailed frame-to-frame capture. It's a tool we used a lot, but it has some lags in the wider perspective when you try to use that. So a way to get around that is to divide your game into sections and then profile them one at a time and then try to compare it. But one thing to note is then when you are profiling a section that is not moving or anything, the profiling tends to stabilize at some point. And with that assumption, we can try to guess that we only need a few frames from each section, which we then can combine into an approximation of the performance of our game. So I'm going to show you a video of a save point profiler, which uses the save point location as the location of sampling. And what we're seeing here is we load a scene, we place the boy, wait for the culling system to settle, and then we do our sampling. And this is done for every save point in the game, and we can see everything calling in and out, and everything moving. So, so back in the editor, when we collect all this, we get this view with the save points and subscenes, a little table of that on top. We have the profiler in the middle. In the bottom, we have a screenshot of the selected save point. So again, a little demonstration of how it works in the editor. We still have the same scripting overview as we did before, and we can still drag the slider in the profiler. Only now, instead of dragging it through time, we are now dragging it through our subscenes and locations. So this has to note a little about this overview is that since nothing is moving in those scenes, it can be thought of as a base cost for each scene. So, and automated testing. Since there's not a lot of manual interaction in this profile run, it's a good candidate for setting up for some automated testing. With that, using an automated build system called TeamCity, which is linked to SVN. And on a daily basis, we would make a build, run the profiler on our target platform, which was the Xbox One, and then copy the result to a server that we could extract from the editor. So aside from always having the latest available profile data, we got a lot of history with an automated build system. So we could track our progression and regression through development. And what we did was we selected a subscene and just took those part of the history and then flipped the axis so you had like a history view of that scene. So yeah, a little demonstration again here of how it looks in the editor. So the same view as before, and now we flip it to a history view. Still the same functionality with the script overview, and now we can drag it through the slide here on top, and we can see how it changes in the screenshot, which is the history of that subscene. So another use of the profile runner was the subscene profiler, which is a profiler that measures the life cycle of a subscene. So this is from when we start an asynchronous load to activation and to deactivate it as well. So how we did that was we disabled all game systems, so character, camera, and just focus on loading one subscene at a time and profiling that. So a little thing to notice is that of course the sampling rate is different because each subscene has different lengths. And one thing that's interesting about this profiler is the end tail, which is where our pre-awake and activation and other time slicing things occurred. So if that spikes too high, we would get a frame spike when loading that subscene. Here's a view in the editor. So what we got out of the profile runner was the save point profiler. It was a good thing for performance overview, which helped us a lot when to focus on our optimization. We have the history profiler that we use to track progression and regression in our optimization, and then we have the subscene profiler to identify load stutterings for subscenes. So another tool we used was the automated playback, which is a replay tool we use for profiling. The automated playback is essentially a controller macro in that we play a section of the game and record those inputs and then use those inputs to replay the same section sometimes later. So a little demonstration of how that works. So here is a save point playback when someone has recorded, so it plays from one save point to another. So it has recorded all the stick movements, the button presses and everything each frame, and then it tries to play back from that save point to another, and when it reaches the next save point, it's tried from the next to the third, and so on. So one thing to note is that since a game is not 100% deterministic, the main character, he sometimes drifts and get out of sync. So to try and prevent that, we had a lot of positional error correction to try and get him back into sync. So, and again, since there's not a lot of manual interaction in the automated playback, it's a good candidate for setting up for automated testing. So again, using TeamCity on a daily schedule, we would generate an automated playback. And this system in itself is a good way to exercise all your game systems, including like the culling system. But where it really shines is when we are able to attach some profiling tools to this system. This was in the way of playback modules that we attached to the automated playback. And so based on events from the playback, it would do some sampling and then store the result on a server. So this is one playback module that sampled the frame rate. So you can see in the graph above, we have a frame rate graph of the entire playback. So where the green bars is where we are below our target frame rate, and the yellow, orange, and red is when we are above a desired frame rate of 60 FPS. And since our game is fairly linear, we could try and map this frame rate graph down into our game below. So one way to do this is that we exposed a lot of the frame rate graph into some of our editor windows. So this is the frame rate graph in the scene view as a line, which maps the traversal of the main character. And here we have it in the subscene inspector for a selected subscene. So we could select a subscene and see how that part of the game was performing. Later on, we added other Framerate modules, playback modules, like memory, subscene events, and audio stats. And here we can see the memory module, which tracks the amount of game objects we have during the playback as the orange line. And at the purple line, we have the allocated heap, which is a source of garbage collection. As we all know, garbage collection is a source of frame rate stuttering. And here we can see we have 4 garbage collections, which we maybe can map up into some of the spikes in the above frame. Another playback module was the subscene event, which is related to a lot what Kristian talked about earlier, which is the state of a subscene during that playback. So the white part is when a subscene is activated, is loaded and inactive and waiting to be activated. The green is when it's within the view frost room, and the yellow is when it's now outside again and waiting to be unloaded. And there's a red part as well, which is when a subscene has been loaded and then unloaded without ever being activated, which could be an indication that some of our visible sets or culling bounds had not been set up correctly. And there's a little fifth one as well, which is the gray, which is the pre-awake time of a subscene. So, and this is the playback the audio module, which monitors or some of our audio events. So, how many audio events we send to and from the sound engine, how many audio objects is moving in the scene, all which has performance impact and effects on audio stuttering. So, just to show you how the setup of the playback modules could look in the editor. So a little demonstration here. So on the right side, we have like the 4 playback modules with the frame rate, memory, subscenes, and audio. And on the left, we have a scene view on top and a gameplay camera below. And one thing we try to do is to mimic the state of the automated playback. So you will select a frame in the playback module, and then it will try to mimic it in the scene view and in the game camera. So we could try and match that up to our automated playback. And just to finish, I'm going to show you development of our frame rate graph. So this is from end of July last year when we began our optimization. This is 4 months later. And this is from start of the summer, just before we went into search. The last one has VSync enabled, which kind of even out all the green bars. So yeah, with this, I'm going to turn it over to Søren.
Hello, I am Søren. I'm one of the game programmers. I've been doing a lot of stuff in C#, and I'll be talking about some of the things we did to optimize our C# code. But before I begin, I just need to do a little disclaimer. I love Unity. And I say that because obviously I do love it, and it's nice to spread the love between other Unity lovers. But also, when you're optimizing, you sometimes get a little bit frustrated, and maybe I have once or twice publicly said that everybody in the Unity team should be thrown into a dungeon and not be taken out until they have tried to release a game with 60 frames per second. So, but I do love Unity, sure. We had this performance budget. We wanted 60 frames per second, and that means that with these things that we had with the streaming, we wanted 4.6 milliseconds for the streaming initialization and the headroom for eventual spikes that could occur. We wanted 2 milliseconds for rendering things like fog and reflections. We needed 1 millisecond for culling, and that left us 9 milliseconds for all the general gameplay and animation updates and particles and all the physics and everything else. So we needed to do a lot, like especially if we have an area like here where we have 18 dudes running around after you, and we all need to do that in 9 milliseconds. So that was a task. And what I will show you is not any C# from the actual game. I've made a little demo script that will show some of the biggest lessons that we learned. And they are very easy to implement. You should all be able to make all the implementations for these tricks to make the C# run faster. I'm doing it in Unity 5.4. Inside was in a heavily modified version of Unity 5.0, but most of them are about the same. I just heard about the new stuff that Unity is doing this morning, and it seems like some of it will be better in 5.6 and from then on, but at least for now, these things will be doable. We have executed it on an Xbox One, where we've done the measurements because that was our target platform, and we did not have IL to CPP in Unity 5.0, but I've been testing this both in mono and in IL to CPP because it'll probably be what everybody's doing from now on. So this is my test scene. I have a very deep hierarchy in the node hierarchy, and then I have an extremely nice character, AAA, with some animation going on. It's not animating, but it has like a mesh and a lot of bones. And this is pretty representative for what you will find in a game where you put the character like deep in a level hierarchy. And on that character, this is the scripts. I have the main script to the left. Is kind of what it does is it's making a list of 100 of these characters, and then it's calling update 1,000 times on every frame, just to get big numbers that are nice to look at. And what it is doing is on the right, you can see we have a character, and it has some floats at the top to control its speed. It has a velocity, and then it just multiplies the velocity vector with the floats and updates the position. And then that is being done 100,000 times each frame. Okay, so whatever I would do when I first wanted to profile things like that is use the deep profiler. Unfortunately, it doesn't really give usable results if you do the deep profiling on the Xbox One. So the deep profiling here is done in editor. Generally, that's okay because the results are mostly comparable in editor and like what we get on the Xbox One. Not always, but you can use that. Yeah, mostly. And if, for instance, we look at this, you can see a lot of numbers and a lot of how much time it takes in deep profile. And I would just take from the top the things that look most expensive. For instance, here we can see that the top one is vector 3 multiply, and it's been done 600,000 times. And that's a little bit weird because we only have 100,000 characters, and they only have one vector that we multiply with some floats. So why are there 600,000 multiplies? But that's simply because I'm so stupid that I've put the vector as the first parameter. So what is going on? The vector takes itself and multiplies with the speed parameter and returns a new vector that is then multiplied with the speed factor that returns a new vector, and so on. So there's 6 vector multiplications in that line up there. So my first optimization would be to reduce those vector operations. And you can see the script on the right. The only thing I've done is I've put in a parenthesis that makes sure that all the floats are multiplied together before the vector. And if you look at the profiler, it has gone from 600,000 multiplications to 100,000. Okay, so here let's look at the results in milliseconds. This is taken from the Xbox One. We have from the mono build 123 milliseconds. And the IL to CPP has 106 milliseconds. And one thing I noticed is I would have actually supposed that IL to CPP was a bit faster, but okay, it's like 12-13% performance increase. So we'll take that. But let's see what happens when I do my optimization. Okay. That's actually quite a lot. That's the only thing I've done. That's the parenthesis. You can go through your scripts and do the same thing and get this kind of optimization just out of the box. Okay, the next thing, use cached transforms. Whenever when you call transform in Unity, it actually doesn't just give you the transform, it does a lot of safety code to make sure that the object has not been deleted or anything. And that is pretty expensive. So what I've done on the right here this time is just cache my transform on my start function to a new underscore transform. And then I'm just using that instead. Extremely easy, you can all do it, and the performance is pretty good. So go ahead and do that. The next one is not always feasible, but a lot of the time it is. It is use local position if you can. On the left, I've been using the normal transform.position, but mostly when I have a character, I don't really care what's in the hierarchy above it. In this case, it was just for bookkeeping that all those nodes were above my character. So if you just put all those nodes to be placed in 0, 0, 0 with the identity rotation, then you can use local position instead of normal position. Or you can reparent your character or do whatever. So in most cases I've worked with, I always use local position. And the results are actually Hadouken! Really wild. Like, that's a lot. And that's because Unity internally stores all data as local positions. So whenever you need a real position, if you want to retrieve it, want to set it, Unity has to go all the way up through the hierarchy and all the way down again to translate from local to world positions. And it doesn't cache it, so it does it every single time. So it's a really good idea to try to keep everything in local positions whenever you can. Okay, reduce engine calls. Whenever you call into Unity, you have to remember that you are working with managed code in C#, and Unity is a C++ engine, so it's working in unmanaged code. So whenever you want some value from Unity, it has to marshal the code and make sure that you copy the unmanaged code to your managed code. So that takes a bit of time. So over here, what I've done is the local position I'm setting. Actually, to the left, you can see I start each frame by getting the local position, and then I set it at the end. If no one else is touching it, I can just cache it myself and just use the cached local position I had from last frame, and then just set the local position once. So that's what I'm doing at the right. So I've removed one call to get local position. And that one call actually takes a little bit of time, which is fine. We can all need all the performance we can get. Okay, so now I said that calling anything in Unity is slow. So would that also be getters and setters? Like, it can be nice to have getters and setters, but does it actually take some time? So what I've been doing here is I've just removed them. My parameters are still public. And let's see what happens. Actually, IL to CPP became more expensive. That doesn't make any sense at all. And I've done other tests where it does get a little bit better, but it's, when you are making something into CPP and then passing that afterwards and compiling that, there's some optimization going on. So sometimes the results can get a little bit weird, and that's probably what happened here. But in all, it doesn't seem like getters and setters are that much of a deal. Like, it seems like it's pretty okay to use those. I get a little bit, but it wasn't one of the big ones. Okay, this one is going to be a little bit ugly. Don't use vector math at all, because we still have 100,000 vector multiplications and 100,000 vector additions. And as I said, whenever you do that, you have to create a new vector, and you have to populate it with data and throw it back in your head. And that takes time. So there's really no nice way to fix this, but on the right you can see what we've been doing. We take the factor, that's all the floats that are multiplied together, and calculate that first. And then we set each x, y, and z member like we're doing there. We simply inline the code manually. It's ugly, but in the end we did this in every inner loop in the entire game, because yeah, as you can see, the performance you gain from that is really wild. Actually, I think we need to zoom in a bit to see better. Bring in the small guys, dude. Here we go. So, sure. So yeah, that's it. That's pretty much. So we don't use any vector math. We just inline everything manually. It's sad, but that's how it ends. Okay, as I said, calling Unity is expensive. So like just getting time, that delta time, that is a call to Unity. So if we just take that and store it globally, so the first function that calls update, it stores a global delta time, and the rest of the functions uses that. Yeah, that can actually give us an increase in performance. So, phew, not much, but why not take it? Okay, for each until the next version of Unity 5.5, but until that, it has been making garbage. And garbage is not nice. We don't want that, so we don't call for each. Apart from that, when you call for each, you're making an enumerator, and you're moving back and forth with that enumerator, and that also is a bit of overhead. So if you can avoid, and you can, it's pretty easy to make a for loop that doesn't use for each. You should do that. So that's what I've been doing on the right, just a normal for loop. And the results are here. Are pretty nice, especially in IL to CPP. Wonder why. Okay, arrays and not lists. This one is pretty fun because inside it actually looked like it was a lot better than when I did this test to take an array and just to take a list and just use static arrays instead. Maybe there's been some optimization done since then. I don't really know, but the idea is simple. If you have an array, replace it with a list. No, the other way around. If you have a list, replace it with an array. So it was not as simple anyway. Okay, but as we can see here, the results are not really fantastic. So maybe that's not necessary. You should do your own measurements if you consider that. Okay, so here we have the results in the end from 106 in IL to CPP to 9.5 milliseconds. That's a factor 11. Yeah, and I haven't been doing anything that changes the game code. I've just like refactored in hand how the C# is written. Oh, what? Oh, I have been cheating. Okay, I haven't really been cheating. Like the optimizations are still valid, but the problem is that I haven't been counting everything. If you look at this code, what I did was I took the factor and I multiplied it to the velocity vector, and then I like set the new local position. The problem is that the factor was 0 all the way through because one of the floats was 0. So the local position is 0 in every update. And when Unity sets the same position as last frame, it skips it, which is nice. It hasn't always done that. But it's pretty nice that Unity makes that optimization for you. But that also means that setting the position hasn't been like accounted for in this test. So how long does it actually take to set the position? Like here we are, 9.5 milliseconds if we're using the same position every frame, and here we are with a new position every frame. So yeah, at least we still got these 100 milliseconds of optimization, but this is pretty sad. So what happens is that whenever you set a position, Unity posts messages down the node hierarchy to make sure that every node knows that it has been moved. So that also means that if you have many nodes in an advanced model, then it gets even more expensive to move it. And the penalty applies once more if you change the rotation. So one penalty for moving, one penalty for rotating. I heard this morning that they're working on improving that, and this is also very, very good and very needed, because this is like, in the end, it turns out that moving the characters was by far the most expensive thing we did, not figuring out what they were going to do, just moving them. And you can't really do anything about it if you don't have source code access. Luckily, we had that, so there are these things we can do if you have that. You can, for instance, set the position and rotation at the same time instead of setting it first position and rotation. That's clever, then you only pay the penalty once. And the sad thing is that that function exists internally in Unity. It's just there. It's just not exposed. So if you have the source code, you can expose this in 2 minutes. And if you sit close to a Unity guy, you can ask him to expose it for the next update, because that would be a nice function to have. There's also get position and rotation. It's the same idea. You get both at once, so you don't have to go all the way up the node hierarchy and back again in one go, and then do it again for the rotation. And as with the other one, that function actually also exists internally in the editor in Unity. They just haven't exposed it. So the same deal. You can expose it, or you can ask them to do it for you. And then actually the last one here, that function doesn't exist. It is, we made a function where we just don't pay the penalty. We don't tell the subnodes that the root node has been changed. The problem is that they need to know, because otherwise they won't be moved. But if you have, for instance, an animation running on your character, which you almost always have, that animation will make sure that the nodes are being touched eventually. So inside, we just moved the character and did not tell the nodes that they were moved, and then the animation system told for us. So we got completely rid of that penalty for moving the character, which gave a speed increase like a factor 8 to 10 from moving characters if we did it that way. So that's also a function that I think could be cool to have, so you can control this and not get the speed increase unless, not get the speed penalty unless you actually need it. Okay, here's a little warning that we fill in. I don't know if any of you noticed that I had a sign function in my demo. Sign, that takes a little bit of time. So we thought maybe we can make a faster sign function by making a lookup table. So we did what you can see on the right, something like that. A lookup table where we put in sign values, and then we have a fast signers function, and we just take the values in our table. And it looked really, really good. Actually, it performed a lot better in editor mode, and also on PC builds. Unfortunately, it didn't perform better on the Xbox One. And we didn't really test it because it looked so good in our PC builds, and that's where we did most of our testing because of the quick turnaround times. So in the end, we actually ended up shipping inside with a much slower sinus function than the built-in one on the Xbox, which was pretty stupid. So the takeaway from that is remember to test your optimizations on the platforms you're actually releasing them for. Okay. I have some basic tips to avoid frame spikes. They don't really have anything to do with the C# code, but don't generate garbage. That's we've said that a few times, and yeah, that will always be a problem if you do. Of course, don't use instantiate at runtime. It's expensive. You must pre-allocate everything, in my opinion. What we found in C#, at least with the mono we've been using so far, is that built-in data structures that are modern, they perform horribly. We found that the list was horrible. It doesn't look horrible anymore. We also found out that dicts, they have a really big cost the first time they're used, which we don't like for spikes. And event subscription is also extremely heavy. So use old-fashioned code if you want it to perform well. And then don't use string concatenations. If you need to concatenate strings runtime, use the string builder class. It's actually fast and doesn't generate any garbage at all. Okay, and then avoid using update and fixed update. What? This is pretty wild because that's the bread and butter of Unity. You have these update functions, you code everything there, it works. But the thing is that whenever Unity calls your update function, it has an overhead. It doesn't show on any of the profilings, it's just there. And it's not even really easy to detect. But you can fix it. You can make your own update manager. You can make it even like inherit something that all your scripts just inherit automatically. And then that update manager just is the only thing that gets the update, and then it passes it on to everything that is like in its own lists of things that need updates. And you should do that. In Inside, we saved 1 to 2 milliseconds per frame by doing that. So most of our scripts were actually being called internally from our update manager instead of taking an update from Unity. Gotcha. Okay, so what did we learn today? Don't use vector math, and cache your transforms, and use local position and local rotation if possible. Reduce your engine calls. Avoid moving objects with complex node hierarchies, and never use for each. Avoid update and fixed update, and kindly ask the nearest Unity developer to expose the faster functions to remove stuff, to move stuff. Okay, so that is actually it. We can take some questions if you want, or we'll be at the speaker's corner afterwards. And Thursday we'll be at Ask the Experts from 9 to 12. Thank you. Yeah, I think there are some microphones.
Thank you so much for all of that. Performance is like a thing that I pride myself in as a technical artist, so all that was like mind-blowing. Avoiding the update. In VR specifically, I have concerns about that. Like, how do you avoid the update when your headset is dependent on the rotation and movement of your camera, like your phone or your VR device? Like, because, you know, I develop mostly virtual reality. I do mobile apps, but like that's more my interest is virtual reality.
Yeah.
So would you have like a separate update to handle the VR input of the camera and then the input of the controllers, let's say, or the environment, or how would you handle that situation?
Probably, we're not doing virtual reality ourselves, so I have really no experience in the problems that might occur there. But that could be a good idea, yeah, to have 2 updates.
Yeah.
Probably.
Okay.
Yeah.
Cool. Thank you.
Mm? Okay, no one else? Is that a question coming or just? Okay.
I can't believe there's not more questions. This has been one of the best talks. It's only the first day, so I mean, outstanding. Thank you guys.
Thank you.
I've heard about a lot of the things you were talking about, like the not using the updates for each. I mean, these are all like low-hanging fruits that all of us could implement. What do you see like in the newer versions? I mean, plus you guys have been working with Unity for some time, so you see the improvements actually happening. What do you think are the best improvements for the latest version, and what is coming down the pipe that you think we should start changing our design paradigms and our coding structures to kind of adapt for?
Yeah, like personally, I'm pretty psyched about the transform thing I heard this morning, that the transforms will now be able to be touched from like threaded code. That sounds like something that can really help you a lot. I don't know if you have anything that you're looking especially forward to.
Yeah, also, the thing that Joachim showed about moving transform on other threads would be really useful. We'll definitely use that for the next project.
Yeah.
To utilize the cores better.
And I guess, there's more. Oh, perfect. Yeah, I was going to ask about camera rendering, but that's, go ahead, rock and roll.
Oh yeah, so thanks so much for the talk. That was incredible. I work on Oriented Blind Forest, which is a stream 2D game too, and you just like solved all our problems. But that's so one of the things we have much more granular scenes where we need to load one like every 15 seconds, 20 seconds ish. So for us, the problem is not just the spikes from integrating it, but also just the total load time. And I was wondering if you had run into that, and if you had done any optimizations to reduce this total load time for a scene.
Yes. So you said you had much larger scenes than we had. Was that correct?
Much more granular. So like we had been loading scenes every 20 seconds. Like you have 3 minutes before loading separate scene sets.
Okay, yeah.
We were just constantly streaming in stuff in and out.
There were issues with Unity, so we did do some optimizations. Some of those that I mentioned in the end, and without those, as one example is that all the instance IDs, when they are updated, that happens on the main thread as it is now, and that actually takes quite a bit of time. So I'm hoping that with the collaboration we have with Unity that we're able to solve some of these issues.
Yeah, that helps a ton too. But it's not just the spikes, it's like the total loading time. I don't know what scene loading time you're seeing, but we had over 20 seconds for some scenes, which meant that you were running up to the edge, and we sort of have to keep the camera back since the scene just isn't loaded yet. And we have to wait until it is loaded. That's
huge, yeah. We only had maybe 1 to 2 seconds of loading time for most of our scenes, actually. maybe you could drop by at the experts session, then we can have a detailed talk and look into your stuff.
Sounds good, but yeah, thanks a lot anyway. Great talk.
Thank you.
Any other questions? Okay. Thanks for the talk, by the way. One thing I use a lot personally is event subscription, and you suggested to totally avoid the built-in one. So what would you suggest as a good alternative?
Like, we made our own lists. Like, we put out, like, you can just do the same and just call it from a list with an interface, for instance. What else did we do?
Yeah, because there's one problem with events, and that's internally they are actually a linked list for, I think it's for multi-threading security. And we didn't use that because all our work is done on the main thread. So we sort of replaced the internal data structure for holding all these callbacks from a linked list into just an array. It gets a little more manually, but then you can really quickly execute these events instead of going through the linked list. And then in particular, in unsubscribing and subscribing in active gameplay, when you have a lot of subscribers, can actually be really slow because you have to sort of rebuild this linked list.
Mm-hmm. That makes a lot of sense. Thanks.
Hi, really great talk, guys. I just wanted to note that this seemed like a ton of work for you guys, and I'm just wondering what your thoughts are, if you would have chosen Unity to do it again, and whether it was like worth it after all that.
Yeah, you did see my disclaimer though, didn't you?
Yeah.
I think one thing that can be said about that is that it has been possible. So we actually were able to do all these hand-tailored optimizations specifically for our game, being a 2D side-scrolling game. So I think that's the strength of Unity, that you can actually do this. And then, of course, we would like to take these lessons learned and then try and improve Unity. So we'll definitely do that. But I think the most important thing is that it's possible. And it's actually, even though we used a lot of time, it's flexible. And I think in other engines that could have been a little more troublesome.
Yeah, also from a gameplay point of view, like in Playdead, we don't really design the games up front. What we do is like we set up things, and then we try things, and then we discard 70% of what we tried, and then we make a game in the end. So the quick turnaround time is really, really, really important for us. And I think for other engines, that would have just killed the other game. Like the quality of the game would have just degraded if we didn't have really quick quality and turnaround time throughout the development.
Cool.
Hi, really nice stuff. In terms of avoiding garbage and avoiding overhead, it seems like you guys have learned a lot of details about how to do that. How can we learn those?
So the question is how you do that yourself,
How do we learn all of those details of avoiding creating garbage and avoiding overhead of different features of Unity and C#?
Yeah, I think that one way that we did it is that we use the profiler again and again and again. So every time we monitor if any garbage is generated, and then in the profiler you can actually see exactly which scripts are generating this garbage. Then you can dive down to see, okay, so it's this for each that generates the garbage, or it's this and that. And then you simply just get rid of every point of garbage going along. I don't know, maybe with the new .NET runtime that they are getting in at some point, maybe the garbage collector would be more effective. We can hope, but
So it's just a question of practice and a lot of work.
Yeah.
Yeah. Oh, well.
Lots of work.
Hello.
Is this one on?
Sorry, just to piggyback off the garbage collection then. So at what point in your development process do you consider profiling your scripts when you have a playable gameplay, when you write a certain set of functions? Like, at what point in your testing phase do you start with garbage collection optimization?
And we did that quite early, actually, to just not let it go completely crazy. But most of the work was done in the last, I think, year of the production. But that has to be held in relation to how long the game actually took to make, and that was 6 years. So I guess that's...
So you did a lot of development. Probably for the first 5 years, you were designing for a little bit more optimization, but then your hardcore optimization happened in the last year.
Yeah.
So you got to hit the performance. Gotcha. So when all the art assets were in, and when you knew where the areas of performance you needed to hit were at.
Can I have that last question again?
So when your art assets and everything was imported into the game and you were creating all the foundation and probably integrating more of the final features, was that where you say you'd start optimizing, or would it be like when the art assets are placeholders, or?
I think most people would have seen the game as being almost complete a year before we actually shipped the game. But then, of course, the artists at our company would not agree. They are really up into the details, but for the most part, the game was actually complete when we did all the optimizations for these things.
Okay. Well, thank you very much.
Yeah, I think we have the time is out. Maybe the last question.
Thank you so much. So you guys did everything under 400 megs, right, in memory?
Yes.
And you also preloaded all your subscenes in that 400 megs first, right?
And that's the mono heap, so it's not the total memory usage for the game, it's only the mono heap that's 400 megabytes.
Right, right. And then, so did you said that you didn't destroy anything, right?
We do object destroy on the hierarchy node, so when we do an unload of a scene, that's actually calling object.destroy on small parts of the scene going bottom up.
Okay, and how does that doesn't generate garbage?
You could say that it does generate garbage, because if there's a mono behavior on one object and you delete that mono behavior and there's no references to it anymore, then it's garbage. But then we just need to make sure that all the amount of scripts and objects that are in the entire game is less than these 400 megabytes of heap space that we had pre-allocated.
Thank you very much.